All right, so now we are going to try to do an example. And I am going to start this example with something very classic, which is the tangent bundle. But we're going to begin from actually the very beginning. So first I'm going to create a manifold, and this manifold will ultimately become the base space, and this is going to be the manifold of S1. So it's a differentiable manifold, so the set will be S1, which is going to be this circle here, and it will have a topology, an S1 topology, and it will have an atlas. So I got to build all of those things. Now the base for the topology that I'm going to propose for this are going to be open intervals. Any little open interval anywhere on this circle, which we're calling S1, is going to be the base of the topology. So any intersection or union of any open intervals, any finite intersection or infinite union of these open intervals will be a member of the topology. And that's how we're going to define the topology. So we've done that. We've got the topology down. Now we need an atlas. So for an atlas, I'm going to divide this thing up into a couple regions, or to several regions. Here's one, so that open region. Here's two, that open region, and then maybe three. I'll put this open region here. And just to highlight them, maybe what I'll do is I'll draw this little red line to sort of highlight the fact that these are the red open regions. You'll notice these open regions don't have any intersections, but I'll solve that problem by introducing some green open regions, and the green open regions will essentially fill that gap and overlap, right? So I want the green open regions to overlap and fill all the gaps. So here's another green open region, and the overlaps can be big, right? You can have large overlaps. Doesn't really matter. So now this is this circle is, we call this S1 because it is sort of the sphere, the surface of a sphere surface of a two-dimensional sphere. Well, the surface of a disk is what it is, and it's going to be a one-dimensional manifold, which is very convenient for this exercise. But this is, so these are now the open sets of the atlas, right? But an atlas is not just a bunch of open sets; it's also a bunch of charts, right? Or I should say, an atlas is a bunch of charts, but each chart is not only an open region like we have here, these red and green regions, but it's also a chart that homeomorphically maps that region to a subset of RD. So let's look at this first one. We'll call that gamma 1. Should try to make my gammas a little better. And one thing I'd like to do is let's characterize every point in S1 by an angle, say theta. So every point in S1 has an angle theta, and we'll call this point here will be theta equals 0. And that's a characterization of the points on the manifold straight up. But it also is a very convenient way of mapping it to the real numbers. So what I'll do is my first mapping to the real numbers will be for this first region here, which we're going to call U1. This red one will be U1. And that mapping, obviously, it's kind of like, if you sort of look at it, you kind of see, well, this is going to have some thetas that are great between some numbers slightly greater than 90, slightly less than, all the way down to something less than, say, 45, right? But it's all going to be greater than 0. But so you know that if we chose this mapping to be simply equal to theta, then the region on the real line that would be relevant would be something like this, where 90 is here and say 45 is there, if we call it in degrees, right? If we use degrees instead of radians. So that might be some sort of degree mapping. And likewise, I could look at U2 and create its mapping, gamma 2, and it goes to the real line. And now let's pretend that this one was theta over 2, theta divided by 2. So this mapping up here was just gamma 1. So I guess the way to write that is like this. You write theta goes to, through gamma 1, goes to theta, like that. And this one, we're going to do differently. We'll say theta through gamma 2 goes to, I'm sorry, I keep saying theta, yeah, theta over 2, like that. So in this case, you might look at, just eyeballing it, I see something as something like minus, say, 40 degrees, plus 45 degrees, so half of that would be 22 and a half, and half of that would be 20, negative 20. So, or actually, instead of negative 20, you could say, actually, why don't we do it that way? So everything is, well, let's stick, because we want to keep this interval here. So we'll say negative 20 to positive 20, something like that. It doesn't really, it's not all that important to zero it down, but it does cross 0. So that would go, that would be this is the manifold mapping for the chart of U2. And likewise, I would go to U3, and I would have gamma 3, and it would go to its own, and then this whole thing, we might consider this to be the high version of it, and we'll say it goes from, say, 200, something like 200 to maybe almost 300, right? The point is, these mappings can be done any way we want. And the transition mapping, for example, in this case, gamma 3 inverse followed by, say, gamma 2, would just be valid for this region in here, which I would call U23. And U23 can obviously be mapped either this way or this way. And the transition between the two alternatives is given by the transition function. And the transition function is clearly going to be a ratio, right? It's going to be whatever ratio it takes to take these points here in this zone, in this intersection zone, which I'll highlight in black, right? These points here, there's just some ratio between the two, and the this point here so it turns out this point here that's 0 is not necessarily part of it. This ratio here is going to actually be this black region at the low end, right, here, and at the high end here. So this transition function is actually going to map from this little part to this little part. And it'll just be some ratio that will correct these, that will correct these coordinates, or convert this coordinate to that coordinate. And now we have, based on this, we just keep doing it for every one of these U's. Right, we do this for U2, U3, U4, we do this for U5, and we do it for U6 and for U4, and we have completed our manifold. And the fact that it's a differentiable manifold should be evident from the fact that this function here is just going to be a very simple conversion of these numbers to those numbers, which is just going to be a multiplication by an appropriate amount, and that is differentiable because it is from the real line to the real line, and you can take that derivative. And so that is how we now create our manifold U1. We've got our set, which is this circle. We've got our topology, which is has a base of all these open intervals, and we have an atlas, which I just explicitly drew here. I just explicitly created an atlas. All right, so let's use this now to demonstrate how to create a tangent space, and then let's use that tangent space to demonstrate how to create a fiber bundle. All right, so begin with, let's start with a tangent space. So I'm going to redraw our manifold. Now I'm not going to include all of the charts, right? We now know that this is a manifold that has its topology. Let's see, problem is S1 gets confused with the commas here. How can I do that? So let's see, so I will go S1, comma, topology of S1, comma, atlas of S1. So that's why we have a differentiable manifold. So here we have it, and we know without drawing them, I'll probably draw them later, but we have these different open intervals. That's what we have, that atlas, and it's the same atlas that I showed you here. So whenever I refer to the atlas, I'm referring to this thing here, these U5s and whatever these gammas are, and I've given some example gammas here. So now let's talk about building a tangent space. Well, in order to understand tangent spaces, if we go back to sort of the basics on it, we remember that it involved a mapping. We need to find, let's pick a point. Let's pick this point here. I'll call that point P. And remember, we talked about all the curves that go through P. So the way we did this before is, of course, we kind of drew a manifold like this at a point P, then we started drawing all the curves that went through P, and then we talked about how we used the different chart mappings to create derivatives with respect to, first of all, the curve parameter, and then derivatives. Then we understood that in terms of the charts, so we ultimately got these expressions that were in terms of the coordinate functions. Well, this manifold here has some arbitrary number of dimensions, but now we've got a concrete thing to look at, and it's got this very nice property that all the curves through P are very simple. They all have the same trajectory, right? Every curve through P essentially looks like that. Now, that doesn't mean there's only one curve through P. There are actually many curves through P. So this, I'll call a curve through P sigma here, and here's our real number line. And the parameter of this curve through P I will call, well, what did we usually call it last time? T? I think T, right? So T. So the curve is actually sigma of T. And so sigma of T will always be in the area of P, will always look, it will always follow this trajectory, because there's really, I mean, it's completely constrained to this circle, right? So there's no other way to go through the point. But you can go through the point at a different speed. So, for example, if you looked at this and you used our previous coordinate system, or I shouldn't call it a coordinate system really, our previous distinction of the points P, you might say, okay, P is located at something like, let's call it 300 degrees, or we'll just use degrees because it doesn't really matter degrees or radians. We'll call it 300 degrees. So if we said that that's at 300 degrees, right, then we might say that this curve that goes through the circle, it picks out the point P such that it takes phi of t equals t. Now sigma of t. Now sigma of t, this has to be a point in the manifold, which we're describing by theta. So what it's basically saying is that theta will equal t. So if t equals 0, the curve is here. And then when t gets to 300, the curve gets to p, right? So in that case, t0 where is equal to 300 degrees, and sigma of t0 equals p, right? This is very familiar from how we describe these curves. This is just one example of a curve. Now, the point is that despite the fact that I only have one possible trajectory, I still have many possible curves. And the reason is because I could do this again, 0, and instead of calling it t, I'd call it, say, s, and maybe I'll call this sigma, I'll call a different function, sigma s. I don't want to, this will be sort of sigma t, how about that? Sigma s of s, maybe that equals 2s, right? So now this curve is moving faster because s of 0 equals 150, right? And so although the curve follows the exact same trajectory, it's moving a lot faster. So it is a different curve. So all of the possible curves, that we can imagine are basically all the functions that are moving at every different speed through that point P. And so there are still, and each of those counts as a different curve. So there's still an infinite number of curves that are going through P. That's sort of the point of that. All right, so now if we remember back to how we built up the tangent space from that lecture a couple lectures ago, we now know that at point P we have the possibility of setting up a tangent space called TP S1 in this case. So it would be TP of S1. So you get an extra subscript because our manifold is actually got a name with a subscript in it. So TPS1. You know what? I'm going to get rid of it. I'm going to get rid of it here though because it's kind of a mess. It'll get confusing. Not confusing, but it'll be tough for me to write. So TPS will now be the tangent space at the point P. And that tangent space has a basis, and it's a chart-induced basis. So whatever chart is at P will establish that basis. And that means that there is going to be some chart from the manifold with some mapping. We'll call this, it'll be the UI chart. That mapping will be gamma I, and it will map to the one-dimensional RD to some region, and that coordinate I'm going to call lambda I, which is the language that was used in the text that I used to learn this example a while back. So lambda I is actually the coordinate. So the point P has a coordinate lambda I. Now, what sometimes is confusing is we're characterizing the point P in the manifold with this thing theta, right? And that actually lives here in the manifold. That's the story of this thing in the manifold. Before theta can actually become a coordinate of point P, I have to decide that gamma I is just the function theta equals theta, right? Or lambda I equals theta. And for me to call this the coordinate, I have to go through this little formal exercise of saying gamma I on this part of the chart is actually just the identity. And therefore, I would write that theta goes to lambda I through gamma I, and then I specifically say, even more so, theta goes to theta, and that ultimately the point being, I guess maybe actually that's not a good way to put it. I should write ultimately lambda I of theta equals theta. That would be like the simplest way of just formally taking this thing, which is actually a way I'm characterizing the manifold directly. But before I can actually call that a coordinate, I've got to go through this exercise, this little exercise. And in elementary GR, you kind of skip that sometimes, right? You skip that step. But I want you to know that it's always in the background. And the easiest way is for this UI interval to be the whole circle, right? If the whole circle is one UI and the coordinate chart is just this straight up unity, then we've done it. It's that easy. But understand, technically speaking, this set has to be mapped into something we call coordinates. And when you throw it down here, it's very tempting to call that a coordinate. And you know, what the heck, it really is. But there is this step in our formalism where we break it up into an atlas, even if it's only a one-chart atlas, right, where everything is just U1 and you only have gamma 1 and it's the identity. You still do that. You still break it up. But now, formally going back and saying, okay, we have some chart with some atlas, and I'm going to erase the requirement that that be the specific chart mapping. We're going to say that there is some gamma I, and we now know that we can create a tangent space there, where the tangent space has a basis, and we call that basis del by del lambda I at P, right? So this is now the basis of, this is the basis vector. It's only, since it's one-dimensional, it only has one basis vector of the tangent space at the point P. And that goes back to our lesson in how to construct tangent spaces, where you use these chart mappings, and ultimately we settled on this notation, which is a bit of a simplification of the notation that shows how the chart mapping interacts with the curve function, right? But this is ultimately what is the basis of the tangent space at P. So, therefore, any member of the tangent space at P, based on exactly what we know, if X is a vector element of the tangent space at S, like that, then we can describe it completely with components, these contravariant components, del by lambda I. Now there's a bit of a problem, right? Because lambda I is, understand, the name of the chart is I. So lambda I is now associated with the chart. And I don't want that here. This I want to be the component, the one component of X. But it turns out I don't need to sum over X, right? Because there's only one. So I'm doing a little too much, because X doesn't need a summation because there's only one, right? So I can now use so understand this subscript I in this story that I'm telling, it's a lone subscript, but it represents the chart map. It's not a space-time subscript like you'd see in general relativity, nor is it intended to be summed. It's actually the name of this variable. And in fact, you know, I could get rid of it if we just understand that we're staying on this one chart, right? And that's fine, because we kind of will for a while stay on one chart. But ultimately we will have we're going to be talking about other charts in a moment, so we have to keep it. So what I could do, though, is I could stipulate that X, this component X here, is the component relative to this chart, right? So why don't I do that? But I'll do that because I don't want to confuse it as some sort of Einstein sum. I'm going to put it in parentheses. So what this is now meant to mean, is that on this particular chart, the ith chart, the ith chart maps to a coordinate lambda sub I, and this is the component of the vector X in the ith chart when using the basis vector that is the chart representative of the ith chart, the chart representative of this coordinate. And then the fact that this thing is all happening at P is all part of the fact that it's part of this this particular vector space, or this particular tangent space. And in fact, one of the ways that distinguishes this weird thing is this is sort of a down coordinate, right? So normally if this was a sum, it would be in the up position. So here it's just a label. This is a way of describing that this is the component in the ith chart. All right, so now without much, I mean, you can now imagine without any trouble at all, I think, that if we went over here to this chart, and that was the jth chart, right? And the jth chart, of course, has its own, its own mapping to R1, but it's now to the jth, now it's lambda j, that some other point, say the point P, point Q, right? The point Q, you would also be able to generate a tangent space at Q in S using the same concept. And its basis vector would be del lambda j, and its normal, and any element of any vector x in that space would be written x j del lambda j. All right, so the point being, of course, that we can create this tangent space at any point in the circle. So every point in the circle now has this associated tangent space. Now let's remember what we were thinking about a fiber bundle now, and see how does this start tying into a fiber bundle. So backing up a bit, or not even backing up a bit, but cleaning up a bit. There's our S1 point, say Q, and we put Q inside one of the charts, which we'll call UI. And of course that chart has its chart map, gamma I, to its coordinate lambda I, which is in R1. But also, we now know that this thing here has TQ of S, that whole vector space, and the basis of that vector space is d del by del lambda I. And any vector will be expressible as x I del by del lambda I. So now we're kind of building up this idea. We want our base space to be this manifold S1. So the base space is going to be S. And we can kind of see that already, because the way the structure is working is at every point in S we have this other structure hanging out. We don't quite, now that, in order for this to become a fiber bundle, that other structure has to be a differentiable manifold in its own right, which we'll show it is in a moment. But ultimately it has to be diffeomorphic to the standard fiber. So the fiber that we're working at is going to be the real numbers. So in order for that to be true, I have to show you that this is diffeomorphic to the real numbers. And you can almost get a sense, right? There's only one, right? It's a vector space with only one basis vector. So there's a real number associated with one basis vector. So that's a real number. So you're going to see very easily that this is going to be quickly mappable to the real numbers. But the typical fiber is going to be a real number. And there's one at every different spot. So we do know that the inverse of the projection operator for any point P has got to be the tangent space at the point P, right? And that had better be diffeomorphic to S. Whoops. That had better be diffeomorphic to the typical fiber, right? That's the whole point. This has to be diffeomorphic to the typical fiber, which in this case is the real numbers. So I need to show this diffeomorphism, and it's appropriate for it happens on each piece of the, so now we're going to have to create we're going to use the same mapping. These UIs will now become the bundle atlas. It's already sort of the atlas of the differentiable manifold, but we're going to use the same one to be our bundle atlas. So now for each UI, I have to be able to show for every point that this inverse projection is going to be isomorphic to the real numbers. And the way we do that is that for each region I, at every point, say x, where x is an element in the manifold, I have a map called h of I of x. And that's a map that takes the tangent space at x and maps it to the real numbers. And these things all have to be homeomorphisms, right? I have to make this homeomorphic between TS and R. So there's one of these for each of these regions, but it's also at every point, right? So it's valid on a certain region, but only at the point X, in this case Q. So this thing will take the tangents, anything in the tangent space at Q, and give you a real number. And the way it operates is very simple. The tangent space at Q has this basis, so it's very simple that h of I at the point X is operating on a vector X, which is an element of the the tangent space at x, right? So this, understand that this is a mapping that takes x, which is an element of the tangent space, and what it does is it basically returns the component of x, right? Which is a real number. So this thing here takes a vector, which is an element of the tangent space, and gives back a real number. And it turns out this is a homeomorphism. It's going to be a nice smooth mapping, or it's going to be a homeomorphic mapping. And there's one of these at every point that makes it so this is true. This is true. Now what about the total space? Well, every point, we're going to characterize the total space in a trivial way for this particular exercise. The total space is going to be the base space Cartesian product with the elementary fiber, the basic fiber. That's going to be our total space. And the projection operator is going to, which is a mapping from the total space to S, the projection will then therefore take any ordered pair of points, remember, because this here represents an ordered pair where one element, the first member comes from that set, and the second member of the ordered pair comes from that set. So this will be like P, well, let's see, I'm using X now for the arbitrary member. So X and, or sort of a little x, right? A little x. This is a little x, right? Where a little x is an element of S. So little x here, and x, which is capital X, which is a member of the tangent space, and that just gives you back little x, right? So now this is our overall structure of the fiber bundle. Now we have our total space, which we've just made this big, massive, trivial Cartesian product of the base space with the typical fiber. We have the inverse projection, which is always the tangent space, but we know that that inverse projection of the tangent space is isomorphic to the typical fiber, or I should say diffeomorphic to the typical fiber, and we have our base space. These are the functions that ensure this this diffeomorphism. So in the previous, let's see, how did this look in the previous way we drew it? It looked like, remember how we did this before? We said we had the base space B, the total space E, right? And then we had a point here, and this was pi inverse of that point, and that maps to the fiber. So now this function that maps to the fiber will be called HI, I guess in this case P, and this is the point P, and in here, this thing in here, that's the tangent space at P of S, right? So now I'm kind of putting some bones on what we did before. The abstract base space is now the circle. The total space is now S cross R, or is intended to be S cross R. Ultimately, it's diffeomorphic to S cross R. The inverse mapping of any point in B is the tangent space at that point, and that tangent space is mapped to the typical fiber through these things we call H. And now what's left? Well, we have to do the concept where we had a region over here, and it mapped over to a region over here, and that thing mapped to S, well, this is, by the way, R in this case, S cross, well, this is the region UI, so this has to map to the trivialization UI cross F, which is R, right? And that mapping we would call pi HI P, using that one notation that we were talking about before. So this is basically it, right? I mean, we're not done, but this is basically how we took that very abstract structure last time, and now this is how we're flushing it out. We're flushing out where this is the inverse projection that is expressed here, and the homeomorphism or the diffeomorphism onto the typical fiber is expressed through this little thing we're calling H, and then this function that is drawn, or this mapping that's drawn as a sort of a pairing of the projection map with this homeomorphism from the tangent space to the fiber, that's written right here, and that takes us to this trivialization. So this is called the trivialization because it takes us to this trivialization region. Now it turns out for this case the entire darn thing is one big trivialization, but we're still breaking it up now into multiple maps for the time being. Okay, so now that we've got that settled, what next? Well, I'm going to, I never shy away from repeating myself, so I'm going to do that here, and we are going to then take the next step and start talking about the structure group and how that works. So since I want everything to be in sort of parallel, I'll call the base space, we'll do that. I'm going to redraw the region, and then I'm going to redraw the total space and its region, and then I'm going to indicate the fiber, which I'll also do in black, the typical fiber F, and you remember we had, of course, pi is the projection, and then the inverse projection, and we know that the inverse projection of a point P, right, is going to be in here, and the inverse projection of UI is going to be pi inverse UI, and then we know that the mapping from inside E to the fiber, right, that mapping we're calling H of I, and then we're calling the mapping from that region, we call that pi H of I, right, because it's that pairing, and that takes us to the very important concept of the local trivialization. All right. So that's sort of the abstract thing we're looking at. So now what have we done? Well, what we've done is we've been working on the circle, right? We've actually been working on the circle. So let's sort of build that thing. And I'll do that with a piece of the circle starting from with this bundle chart, which will be U1, and of course there'll be an overlapping bundle chart because these stories about overlaps are always very, very important with this. In fact, they're a defining feature of all this. And this bundle chart will be U6, right? So you can kind of imagine there's another bundle chart here which goes that way, and that's U2. And then this whole thing goes all the way around the circle. But we're going to focus on this U1, U6, sort of where it comes back. But they're all the same for the purposes of what we're doing here. This region in the middle, of course, will be U61, that intersection region, and we're going to focus on a point that's squarely in both of those regions. So the correspondence here is that this U1 could very well be UI, and its projection, the projection of UI into the total space is this pre-image of UI. And so there is such a pre-image of UI. Let's concentrate on the point first. The pre-image of the point is this little region in the total space, and we know that the pre-image of the point is equal to the tangent space, right? So in this case, we should have a look, we should write that down. This thing through pi inverse of P, say we'll call that point P, notice point P, by the way we're defining it, lives in the base space, and this is going to be our base space, S1. So it's S, it's going to be our base space. So pi, well, that is the tangent space at P, right? The tangent space of P, but we have to kind of decide which way are we going to project it. Are we going to project it using U1 or U6? And this is important because U1 has coordinate system lambda 1 and U6 has coordinate system lambda 6. And the mapping, the chart mapping, meaning the differentiable manifold chart mapping, which would be gamma 6 for this chart, and it would be gamma 1 for this chart, that's going to map this thing to, that's going to map this thing to the real line, lambda 1, right? That's that chart mapping. And ultimately, you remember that that ultimately gives us a basis for the tangent space at every point in U6. Likewise, every point in U1 will be assigned a basis in the tangent space, but that basis is driven by the U1 coordinate, which is driven by the gamma 1 chart map. So if P comes out of here through the gamma 6, it gets projected to the tangent space, well, that tangent space is going to have a basis del lambda 6. But likewise, it could come out with the same inverse mapping, and it's still the tangent space at S, but it ends up with del lambda 1. And that's okay. I mean, there's no problem with that. They're both equivalent. They're both completely legitimate and equivalent mappings. They just happen to overlap at P, which is not uncommon. And in fact, it's typical. So, but these mappings here, right, these mapping here corresponds to this red region getting mapped into this red region. Or, I'm sorry, it corresponds to this point, the pre-image of the point in the base space landing in E. Well, that's what this is. This tangent space here is part of E. And this is the pre-image of this point. And in this case, when you do this, when you identify this tangent space, you're identifying it with this chart, so it has a different basis than over here. So ultimately, any vector, so now that we're in this tangent space, we have to project that tangent space homeomorphically onto the fiber, right? That's what H does. H takes any member of this pre-image of a point and delivers it right into the fiber. So I need a mapping from these guys into the standard fiber, which is the real number. But we've already decided what those mappings are. Those mappings are going to be called, in this case, H6 at P, and this mapping is going to be called H1 at P, and it will give us X, the coordinate, or the component X6, and this will give us the component X1. And those mappings are exact analogs of these over here. That's what H6 is, and that's what H1 is. Now we've chosen all of our H's for what we're going to call the tangent bundle. We define what these H's are. We define how these homeomorphisms work. And in our case, all the HI's at any point X in the base space, remember X is a element of S in this case, all that does is it takes any vector, capital X, and just returns its component. Its component. And that is a mapping. That's a mapping from the tangent space, because X is an element of the tangent space, to the real numbers. And that's exactly what you need, because the pre-image of a point is the tangent space, and then you have the homeomorphism of that to the real numbers. And of course, the real numbers, by the way, are a manifold. So the fact that it's the fiber, which must be a differentiable manifold in its own right, that's definitely what it is. So that's what these guys are. And now the question is, well, what about UI getting mapped to this region here, the pre-image of the whole chart region, and it's getting mapped to the trivialization? And that happens here also. I'll just draw it this way. This function is going to be called pi hi. Right? Pi hi, well, I shouldn't make it hi, right? Because we're dealing with something particular. I'll do pi h1. And pi h1 is a mapping from this entire region here, this entire thing. God darn it, that's not looking very good. Let me try it a little more. So pi hi is going to map pi h1, that is going to map u1, which is this whole region here, and it's going to send that to something that it's going to make that diffeomorphic to u1 trivialized with the fiber, which is r, right? And that's what pi h1 is. So this now, this here, this mapping, taking all of the u1 and mapping it trivially to ui cross r, that mapping is called pi comma h1, and that's what this mapping is. And likewise, obviously, there's the same thing from 6 to u6 trivialized with the fiber, and that's called pi h6. So I've taken this abstract thing we've talked about in our last section. You know what I'm going to do? I'm going to try to use a feature of this. I'm going to take this, I'm going to shrink it a little bit. Hope it's not too shrunk. And I'm going to move things around so we can spend more time seeing our, well, it's not going to be perfect. So this is a little bit off the page, but we don't need to look at this too much right now. We got to focus more on what's going on down here. So we've made everything parallel to this. We now need to talk about the transitions between these two bundle mappings, right? Because what you have is you have mappings from F to F. Likewise, you could think of it as mappings of the trivialization to the trivialization. And those are these transition maps that would take you from this number here to that number there, because you're in a region where you could go either way. So this must be a very simple thing to do. And indeed, it's just, I mean, this is a real number and you're converting to another real number, so you're just multiplying by a ratio. You're multiplying by a number, and that number, to go this way, is going to just, we're going to call it R61. To go this way, you're going to call it R16, and they're going to be reciprocals. But R61 and R16 are numbers. They're simple numbers that will convert this process into this process. And those simple numbers are transition functions, which means they are defined, R61 would be defined as H6 at P inverse combined with H1 at P, and that would be equal to the real number R6 to 1. R1 to 6, of course, it goes the other way, H6 at P after H1 at P inverse. So those are the two transition functions, R61 and R16. And it's not a transition function, remember, so we're using the word transition function in two different ways, right? We're using it to talk about the transition of the differentiable manifolds charts in this region, which converts the coordinate lambda 6 to the coordinate lambda 1, and we will indeed talk about that in a moment. Those transition functions define differentiable manifolds because they have to be smooth and differentiable. Now, what we're going to demand is these transition functions have to be members of something that we call the structure group, right? It has to be part of the structure group. Because what the transition functions are is they're maps from the fiber to the fiber. And maps from the fiber to the fiber, since the fiber is a differentiable manifold, it's maps from one differentiable manifold to another differentiable manifold. And it must be a diffeomorphic map, and the set of all diffeomorphisms between F and F is usually written in mathematics books as diff F. And the point is that these transition functions are elements of the diffeomorphism group on F, right? They are among all of the possible diffeomorphisms from F to F. In this case, F to F is just R to R. Well, what is the total diffeomorphism group from R to R? Well, the diffeomorphism group is R itself except for 0, right? So R minus the element 0, any of those numbers you can take and multiply you can take an element of R, multiply it by an element of this diffeomorphism group and get another element of R. And for every element of R, you can do this in a way that this mapping is a diffeomorphism. So all the real numbers except for 0 are elements of this diffeomorphism group. And in our particular setup, we've discovered 2 real numbers. And those 2 real numbers must be part of the structure group. Now, you could argue that the structure group, well, it's just the diffeomorphism group from F to F, because these two numbers are certainly a member of this diffeomorphism group, right? So that's not saying too much, right? Because I just throw this into the bin of all these numbers and I've got the structure group. But that is considered a structure group for this thing. It's just that if I have 6 intervals, right? So 6 intervals will give me one overlap. Every possible overlap that exists will give me a real number. The problem is if I accumulate all those real numbers, R1, 2, R2, whoops, R1, 2, R2, 3, R3, 4, R4, 5, R5, 6, R6, 1, and then the reversals too, right? That's not a group. This is not a group because these numbers are completely arbitrary. And why are they arbitrary? They're arbitrary because the ratio of this component to that component that establishes what this transition function is, well, that ratio is set by these lambdas. And if this lambda and these lambdas are set by these gammas, and these gammas are essentially arbitrary. So the real question ultimately is what is the rate of change of lambda 1 with lambda 2? In this region here, if I move along and find the lambda 6 coordinates, I say 1 to 2, I meant 6 to 1, right? 6 to 1. If I move along this region here, and lambda 6 could be growing, but lambda 1 could be shrinking, right? In which case this is a negative number, or it could be, or they could both be growing or shrinking together, in which case this would be a positive number. Lambda 6 could be changing very rapidly, and lambda 1 could be changing very slowly, in which case this would be a large number. So, or the opposite, in which case this would be a small number. The point being that is what sets this component, right? Is the nature of these mappings set the size of this component in our one-dimensional tangent space. And once these components, if their sizes are set differently, which they usually will be, then these real numbers are just arbitrary numbers that compensate for all of that. The point is those arbitrary numbers, when thrown into a set, don't form a group. If I multiply 2 of them, I'm not going to necessarily get a third. And it's not closed under multiplication. And that's, I mean, if a group is nothing else, if it's closed, right? So that's not good enough. So I need a bigger structure group of which these things are part. And one that will work is all the real numbers minus 0. And that will give me the total latitude. I can choose the lambda 6 and lambda 1 any way I want. And the structure group will contain all the transition functions that I can think of. However, I can also be more clever than that. That is, I can actually choose lambda 6 and lambda 1 in a very, very clever way that makes the structure group smaller, meaning all the possible transition functions for the design I make of my particular atlas will be such that I don't need the full diffeomorphism group. I don't need all the real numbers minus 0. I can make it so all these ratios are positive. And the way I do that is I say, okay, lambda 6 is going to be increasing in this direction. Lambda 1 is also going to be increasing in this direction. Same with lambda 2. And I have all the lambdas increasing in the same direction. And if I do that, these numbers will always be positive, and these ratios will always be positive. And that is good, because what will that do? That will mean I can take all the possible transition functions, which are just these real numbers in our case, and I can take all those possible transition functions, and I'll notice they'll always be positive numbers. So I don't need all the real numbers, minus 0. All I'll need are the positive ones, right? And that's a much smaller structure group, so that's really good. So the structure group of this fiber bundle is actually much smaller than this. It's actually just this, because this is possible. It is possible for me to make an arrangement, an atlas. So I'm now looking for the smallest possible structure group. So I've done well there, but I can take it a step further, and I can make sure that all of my gammas on the underlying base manifold are chosen in such a way that they change at the same rate, right? They change at the same rate, which means the components in this chart region and the component in this chart region are going to be identical. These are going to be the same number, right? In which case, these ratios are always going to be 1. And that is the smallest structure group that I can come up with. The smallest structure group is just going to be 1. And now, that is the only possible, for that circumstance, where all of the lambdas are increasing in the same direction, and they're all increasing at the same rate. Therefore, all these ratios will always be 1. All the transition functions will be 1. Now, when I throw that 1 in a set, it is its own group, right? Here the problem is the group wasn't closed. Now, if I design it that very, very clever way, I end up with just the identity as my one group element of my structure group. And whenever the structure group reduces to the identity, you now know that your entire manifold, your entire fiber bundle is trivial. Remember, this is all about fiber bundles. Now, the fiber bundle is a differentiable manifold, but it is a trivial one now. If you can cleverly reduce the structure group to 1. And in this case, you can. And that's true of all tangent spaces. Now, the way this generalizes to other tangent spaces is actually pretty interesting. The diffeomorphism group of F onto F, which is R to R, is just R minus 0. Now, generally speaking, you're going to have higher dimensional vector spaces in your tangent space. This is just one dimension, right? But you can easily imagine, well, almost all other, in general relativity, right? You're going to have tangent spaces that have 4 dimensions. And so now you need the diffeomorphism group between a 4-dimensional vector space and another 4-dimensional vector space. And that's called the general linear group of 4 dimensions. And it's still, the most general structure group is still going to be something like this, but instead of, it's going to be, well, I guess I can write it down. It's going to be the general linear group in 4 dimensions minus, the general linear group in 4 dimensions is all the matrices, the linear matrices that connect in 4 by 4 matrices, but it doesn't include the matrices that have determinant of 0. In this case, when you come down to 1 dimension, it ends up being R minus 0. We'll talk about that later. So anyway, so by reducing the structure group to nothing more than the unit element, we've sort of shown that our design of this whole thing is trivial. And of course that makes perfect sense because we actually intended it to be that way. We started with a total space that was trivial. It was S cross R. We had a fiber, which was R, and we had a base space, which was S. We had our pi took a point in S and a point in R and just returned the point in S, and the inverse of the point in S was the tangent space at the point P and S. And then we defined all of the HIs, right, at all different points to simply take a vector x and return its component in the ith chart. And that is the fiber bundle called the tangent bundle. This whole thing is called the tangent bundle. And we've exemplified it in a one-dimensional manifold of S1. Now, the last thing I want to mention is it didn't have to be this way, right? There was something we could have done a little differently, and it has to do with this definition right here, where all of the homeomorphisms between the tangent space and the fundamental fiber F, right? The fundamental fiber F and the tangent space T. We set it so you just strip off the component. I could have set it up. I could have set it up so that H1 of X through H5 of X do exactly that. Strip off the component. But H6 of X was different. It takes X and it gives you the opposite of the component. And that is a different group, right? That is a different thing, because now, no matter what I do, no matter with that rule in place, no matter what I do about designing the manifold using the same rate of change here and using the same directionality, reducing it, no matter how much I work to reduce it, I can't get this far. The best I can do in that circumstance is I can get to the group -1 and 1. And that's a different group. That's isomorphic to something called Z2. And that is the equivalent to an infinite Mobius strip, right? Because I no longer can jam everything into the trivialization. And what this basically means is that the core, the underlying total space is no longer just S cross R. I've actually created a different total space that's not S cross R. And I've done that simply by demanding this homeomorphism be different in H6. And I've created a Mobius strip. And in my next lecture, what I'm going to do is I'm going to go through the Mobius strip in a little bit more mathematical detail. It's not going to be through the tangent bundle, however. But I want you to understand that's the distinction between that little change, right? That little change is all the difference, because I can no longer reduce this to the trivial bundle. I now have a different structure group at its foundation. And that different structure group basically changes the whole thing. It's no longer the tangent bundle. All right, so that's our big example of a tangent bundle, and our first example of a fiber bundle, and our hint about going beyond a straight up globally trivial fiber bundle. Knowing trivial fiber bundles is almost enough, I got to say. But it's just too tempting to talk about the non-trivial ones. So the next lecture will be a little bit more about the Mobius strip.